Hello, my name is Lauren, and today I'm going to be showing you how to graph trig functions. So the two that we're going to be looking at today are sine and cosine. You'll be learning how to write equations and graph them. Let's get started. So we're going to be starting off by looking at the parent function of sine. So that just looks like in an equation form, y equals sine times x, as you can see here, and then graphing it, it looks like a pretty simple wavelength. It starts in the origin of the graph and goes out with a range of 1 to -1. And the x-axis of this graph is going to be labeled a little bit differently from how your regular graph might be labeled, and it relates specifically to the unit circle, which I'm going to explain in a minute. So as you can see, each of these values, pi over 2, pi, 3 pi over 2, and 2 pi all relate to a certain number of degrees. So for instance, pi over 2 is 90 degrees, or pi is 180 degrees. So each of those relates to a certain number of degrees, which then corresponds to our unit circle. And if you think about it, each one of these wavelengths, each of these represents a radian on the unit circle, as you can see here in this picture. Now we're going to be looking at the parent function of cosine, which is y equals cosine times x, and it is basically the same concept as sine. However, there is one major difference, which you can see when you graph it, which is that the graph does not intersect with the y-axis at the origin. Instead, it intersects at about 1. As you can see here, we still have the same concept with the unit circle and the labeling of the x-axis. So in our trig functions, there are several variables that can be manipulated and are used to describe the appearance of a graph. They're also used to describe an equation or just a trig function in general. One of these is called the period, which is the distance over which a curve repeats itself. And if you look at a graph of a cosine or sine function, you'll see that it is made up of many of these little curves, and the distance of one curve is equal to the length of a period. So as you can see here, we're just looking at how different lengths of periods have effects on the appearance of graphs. So with a small period, the graph is much more condensed, and a long one is more spread out. Now we're going to look at how you fit periods into equations. Now that we know what a period is, we're going to look at how you put them in an equation and how you use them to manipulate a graph. So let's start with our parent function, y equals sine of x. Now we're going to add in a new value, b. Now b is instrumental in finding our period. So we're going to take 2 pi, a very important number here, and divide it by the absolute value of b to get 1 period. 2 pi is a pretty important value in trigonometry and the unit circle, because if you put any point in the unit circle, the distance that it takes to get back to that point by going around the circle is 2 pi. 2 pi is also the assumed period if there is no b value. Basically, 2 pi represents the distance of one cycle. And so by dividing it by b, we are manipulating that to make our periods longer or shorter. Now we're going to look at another element of our trig function, which is amplitude. Like period, amplitude can be used to manipulate and describe a trigonometric function. Amplitude describes the length or height of each wave. Each wave has the same length or height, and it can be found by taking 1/2 of the difference of the minimum and maximum of your graph. So the minimum and the maximum, as you can see here, are basically the highest and lowest points that the graph hits. You can also find the amplitude simply by looking at how many units above the x-axis the highest point is. Now, how do you put that into our equation? So let's start out with our parent function, y equals sine times x. Now we're going to add in a new variable, a, to make y equals a sine of x. And A represents the amplitude of the graph, or the function. Additionally, the default value of the amplitude, if there is no A written into the equation, is simply 1. It's also important to note that the amplitude is measuring a distance and therefore cannot be negative, so you can always, or you should always, take the absolute value of whatever you get for your amplitude, either mathematically or through your graph. Now let's put everything that we've learned so far together, combining our knowledge of periods, amplitudes, and the functions of sine and cosine. So let's start out by putting them all into an equation. What would that equation look like? Well, we're going to start out with the base of y equals sine of x, and now we're going to add an a for the amplitude and b to represent the period. Now let's put that into an example. For instance, we could have y equals 1/2 of sine times 2x. In this case, 1/2 would be the amplitude and 2 would be the period. Now we're going to look at what that looks like on a graph. So here we have our x and y axes, and we're going to start by drawing a simple wavelength, and you can see on this wavelength we're going to illustrate the period, what that is, and then we will look at what the amplitude is on this graph. So you can find the amplitude either by taking the distance from the bottom up to the x-axis or down to the x-axis. Make sure you're taking the absolute value. Either works. Now let's look at our final two factors, which, like amplitude and period, manipulate and describe our trigonometric functions. These two are phase shifts and vertical shifts. A phase shift moves the graph from left to right. How would that look on a graph? Well, let's see. So here in this graph, the dotted line represents the parent function or the parent graph, so what the graph would look like without the shift. And the blue line represents what it looks like with the shift. As you can see, it has been shifted to right. Now let's look at how we would describe a phase shift in our equation. So again, starting with our basic equation y equals sine of x, we're going to add a new value, keeping it in parentheses with the x. This new variable is c, which represents the phase shift. If you're given an equation, you can calculate the phase shift by taking the opposite of c and dividing it by b being the period length. Our next variable is a vertical shift, which moves the graph up or down. As you can see here, the purple line represents, once again, the parent or original graph. Now, the green line has been shifted upwards using a vertical shift. How does this look in an equation? Well, once again, starting with our simple y equals sine of x, we're going to add a new variable, d. D requires no equation or no changes. It is simply the vertical shift. Now, putting it all together, once again, we're going to add in our two new values that we just learned, c for phase shift and d for vertical shift. Now that we understand the basic concept, let's work through a couple of examples. So take the equation y equals sine of 2x minus 3. And we're asked to find here the amplitude, period, phase, and vertical shifts, as well as construct a graph of what this would look like. So the amplitude we know we can find by simply looking at what is in front of the sign. However, there's nothing there, and as we see here, the default amplitude is 1. For period, it's a little bit more complicated. We take our b value, and if you remember from before, and we'll go back, b is 2 pi divided by the absolute value of b. So we're going to do that, and in this case, b is 2. So the 2's cancel out on top and bottom, and our period is simply pi. to find the phase shift, we're going to take the opposite of our C value, which is positive 3, and divide that by our B value, which is 2. And now for the vertical shift, there isn't one because there is nothing written outside of the parentheses that is being added or subtracted to it. Let's look at one more example together. So here we have the equation y equals 1/2 of cosine times 3x plus 4. We're asked to find the amplitude, or the height of each wave, the period or the distance between each cycle of waves, the phase, or the amount that the graph is shifted to the left or the right, and the vertical shift, or how much the graph is shifted up or down. Let's start by looking at the amplitude. The amplitude comes right before the sign and is simply 1/2. Now, the period is a little bit more complicated as we have to take the 2 pi and divide it by the b value. This cannot be simplified, and our period is 2 pi over 3. Our phase is 0 since we aren't adding anything to the 3, and our vertical incline is simply 4. Now, let's look at graphing this. We're going to start by labeling our x and y axis, making sure that we're using numbers that correspond to the values in our graph so that our graph is not too high or too small or too big. And remember to keep the values on the bottom the same. Now we're going to look at this graph, which starts at 4 on the y-axis because it is a vertical shift of 4 and goes down by 1/2 since that is our amplitude. To close off our lesson, now that you have a basic understanding of how to graph and use equations with trigonometric functions, here are 2 practice problems to work on by yourself. Find the period, amplitude, phase shift, and vertical shift of the following 2 equations and graph them. Good luck and thanks for watching. Bye.